We are asked to find the exact length of the curve y equals the natural log of the cosine of x as x goes from 0 to pi over 3. I'd like for you to pause here and see if you can come up with the answer. Alright, so here we are. The derivative of the natural log is 1 over the argument, and then times the derivative of the inside function if applicable. Since the argument is cosine of x, the derivative is negative sine of x, and so y prime actually boils down to the negative tangent of x. So 1 plus y prime squared is 1 plus the tangent squared of x, which happens to become the secant squared of x. Square rooting that gives us a length of the integral from 0 to pi over 3 of secant of x dx. As you may recall, the integral of the secant of x is the natural log of the secant of x plus the tangent of x. And we're going to evaluate that from 0 to pi over 3. The secant of pi over 3 is 2. And the tangent of pi over 3 is the square root of 3. If ever you struggle with that, I would recommend you draw just a quick version of the unit circle. Here we're talking about quadrant 1. Pi over 3 is the angle at 60 degrees. And we can see here that the cosine would be 1/2. The sine would be the square root of 3 over 2. And that's where I'm getting that the secant is 2, the reciprocal of 1/2. And the tangent is the square root of 3. Because we have the y coordinate divided by the x coordinate, the 2's divide out. Finally, putting 0 in place of the tangent function gives me a 0. 0 in place of x in the secant function gives me 1. The cosine of 0 is 1, the secant is the reciprocal, and the natural log of 1 is 0. Therefore, our length is the natural log of 2 plus the square root of 3. That's the quantity in the argument of the logarithm. Next up, same instructions, new function. Our function is y equals 1 minus e to the x squared. Our interval is from 0 to 2. Let's do this together. Y prime is equal to e to the negative x, because the derivative of 1 is 0, and we're using the chain rule, so the term becomes positive. Therefore, 1 plus y prime squared is going to be 1 plus e to the negative 2x. I'm not sensing anything nice is going to happen here like we've seen in some previous examples. The length is going to be the integral from 0 to 2 of the square root of 1 plus e to the negative 2x dx. Here's the thing. If we had an e to the negative x out front, then we could consider a direct u substitution. We don't have that, but we're going to try a u substitution anyway. We're going to let u equal e to the negative x. And right now you're wondering, why don't I let u equal e to the negative 2x, or the entire radicand? If we try that, then we're going to run into a problem when we find du. Go ahead, write it down, see what happens. We still have a problem here when we try to find du, but it's one that we can deal with. Du will then be equal to negative e to the negative x dx. Well, here's that aforementioned problem. I don't have an e to the negative x, let alone the negative part. I mean, we could fix the outside negative. What I can do, though, is I can replace dx, provided I'm careful with how I treat du equals negative e to the negative x dx. What I'd like to do is I'd like to get an expression for dx that involves only u. I'm going to divide by negative e to the negative x, but not in such a way that I mix my variables. Dividing still means I'm going to have du in the numerator. But then if I divide by negative e to the negative x, well, e to the negative x is the same thing as u. So in fact, what I'm going to do is I'm going to divide by negative u. You see, on the side where I have an x, e to the negative x is e to the negative x. On the side where I have u, I'm using the relationship u equals e to the negative x, so I haven't mixed my variables. The result is that I can write down the integral as the square root of 1 plus u squared. And then when I replace dx, I'll replace it with negative du over u. I'm going to write that as u in the denominator, negative out front, du. You may notice I didn't write the limits of integration. For the limits of integration, we need to use the substitution that we've seen. I almost had a color crisis there. We had limits in terms of x. We need limits in terms of u. X went from 0 to 2. Since u is equal to e to the negative x, when x is 0, u is 1. When x is 2, u is e to the negative 2. Those become our new limits of integration. Remember that at the very same step that we change our variable for the integral, that's when we change our limits of integration. You may have noticed that our integrand now has a square root of 1 plus u squared. That lends itself to a trigonometric substitution. That's one of the reasons that I identified u to be e to the negative x instead of e to the negative 2x. It's kind of a recognition that here I have a pattern of 1 plus something squared. As for the trigonometric substitution, if I have the square root of 1 plus u squared, then I'm going to flesh out my triangle, and we may be thinking about a substitution that involves a tangent. At least I hope we are. So I'm going to flesh out this triangle here and let u equal the vertical side, 1 equal the length of the horizontal side. And then the hypotenuse is the square root of 1 plus u squared. And you may recall that setup indicates that u is equal to the tangent of theta. Based on that, we have that du is equal to the secant squared of theta d theta. And based on the triangle, we have that the secant of theta is equal to the square root of 1 plus u squared. Remember, I want an expression that involves the square root and not the other variable. We can then start to replace some values in the integral. The square root of 1 plus u squared is being replaced by the secant of theta. The u in the denominator is going to be replaced by the tangent of theta. And du is going to be replaced by the secant squared of theta d theta. See if I can fit it in. I did. I don't like the way it looks though. So there we are. Now I really don't like the way this integral looks. We have the secant of theta over the tangent of theta times the secant squared of theta d theta. Furthermore, we need to deal with the limits. Our u went from 1 to e to the negative 2. So now we need to figure out what that means for theta. If u is equal to 1, then theta must be pi over 4, because u is equal to the tangent of theta. If u is equal to e to the negative 2, I have no recourse but to use an inverse tangent. So theta is equal to the inverse tangent of e to the negative 2. So those become our limits of integration, pi over 4 to the inverse tangent of e to the negative 2, which looks terrible. Again, so does the integrand. As it turns out, the secant of theta divided by the tangent of theta, well, tangent is the sine over cosine, so I'm going to multiply that by the reciprocal, the cosine of theta over the sine of theta. And then here we have times the secant squared of theta. Why not everything in terms of sines and cosines? Didn't feel like it. But I do see that the cosine will divide out with the secant. Now, what to do about this? Well, we end up with the secant squared of theta times the cosecant of theta, which isn't nice at all. We can do this using integration by parts. At this point, you may be thinking, I want to bail out of this. We've already substituted twice and this isn't really getting any better. I have good news for you. We can bail out of it. So at this point, I'm just going to draw a little face that says, I don't like how this is going. And we're going to start fresh again with the integral that we wrote down with the u's. All right, so I've rewritten that. And at this point, I'd like to remind you that we saw how to look up stuff like this in a table. So let's bring in that table. I have here in the reference pages forms involving the square root of a squared plus u squared, because that's what my radical looks like. And I see what we're looking for in number 23. We have the integral of the square root of a squared plus u squared over u du. That matches what we've got. So I'm going to blow that up a little bit. And we'll say that our length then becomes the negative of, which one was it? That one. The square root of a squared plus u squared minus a times the natural log of the absolute value of a plus the square root of a squared plus u squared divided by u. Our table has it as an indefinite integral, so there's a plus c. But here I'm going to make this a definite integral, because that's what we have, from 1 to e to the negative 2. So let's note here that this is table. It was form number 23 with a equals 1. And now let's finish this off. Evaluating e to the negative 2 in place of u is going to give me L equals minus in front of the whole thing. We'll deal with the symbols, grouping symbols in just a minute. The square root of 1 plus e to the negative 4, because that's the square of e to the negative 2, minus the natural log of 1 plus the square root of 1 plus e to the negative 4 divided by e to the negative 2, absolute value. Now, we'll keep going in a minute. That's a log of a quotient. We're going to turn that into a difference pretty soon here. Minus, so all of that is evaluating for e to the negative 2. Now we need to put in u equals 1. So minus the quantity of the square root of 1 plus u squared, so 1 plus 1, minus the natural log of 1 plus the square root of 1 plus u squared over 1, and then we're going to group all of that together there. And again, these second ones are what happened when we put in 1 in place of u. Now we're going to deal with this quotient here. We're also going to distribute the negative. So L is equal to negative square root of 1 plus e to the negative 4 plus the natural log of 1 plus the square root of 1 plus e to the negative 4. You'll notice I dropped the absolute value in favor of parentheses just because we didn't need the absolute value. And then we're going to have minus the natural log of e to the negative 2. You see the negative in front of the negative makes that a plus, but then this is a quotient, so minus that value there. Now this negative distributes to this negative over here, so effectively those become plus. And I'm left with essentially the same signs as what I have over here. So negative plus square root of 2 minus the natural log of 1 plus the square root of 2. And as I said here, we can deal with, maybe I didn't say it, the negative natural log of e to the negative 2. That becomes 2. I'm going to write all these with positive values in front here. So looks like we've got the square root of 2 minus 2 plus the natural log of 1 plus the square root of 1 plus e to the negative 4 minus the square root of 1 plus e to the negative 4 minus the natural log of 1 plus the square root of 2. Now if you really wanted, you could combine these logs into a single quotient. I'm not going to bother. This is our final answer. Now, I went through all of this really for a couple of reasons. Number one, to remind you that we have trig substitution and what that looks like. Number two, I said a couple of reasons. I'm going to count to more than two. Identifying the u, if we're making a substitution, can be tough. But if we can remember that we do have forms that look like 1 plus u squared, then that might help in our choice. And again, if you didn't do it before, try letting u equal e to the negative 2x, or the whole radicand here, and you'll see that you run into trouble. Another reason was to see how we deal with finding a dx for our substitution if I can't get rid of a factor of the derivative, right? And it's that if I need to divide, I need to make sure that I'm keeping like variables together. Finally, the fourth of the two reasons is to remind you that we have these tables. And so if an integral just looks really terrible, I want you to think about the fact that there are those tables, and maybe you'll be able to find a form that works for you in them.